Good morning, dobre utro, buenos dias, bon matin, and guten morgen. Welcome back to the RedMars Podcast, where we take the wonders of space technology and bring them down to Earth. I'm your host, AstroJake, and today we're diving into one of the most fascinating tools in humanity's exploration of the cosmos. Yes, we are talking about space telescopes. From their engineering marvels to cosmic discoveries, they enable everything we see in space. So we'll cover it all, so buckle up and get ready to gaze into the deep universe. Alright, so what exactly are space telescopes and why are they even important? Well, space telescopes are essentially observatories, but in orbit. They're built to capture light and other types of radiation without interference from Earth's atmosphere. Why do they matter so much? Well, because down here, our atmosphere, while great for breathing, is terrible for stargazing. It blurs light, blocks wavelengths like ultraviolet, X-rays, and gamma rays. Space telescopes help us see the universe in unparalleled clarity, giving us insights into galaxies, black holes, and even the origins of the universe itself. Now, when you look up at the night sky and you see that kind of twinkle or kind of wonkiness of a star where it kind of looks like it's maybe moving around a little bit or flickering, or you might think, no, that's a plane, not a star. That's due to the atmosphere causing some sort of distortion through the actual image that you're trying to see. So by putting these telescopes in orbit and in certain places around the Earth, we are able to get outside of the atmosphere and remove that distortion. So, for example, thanks to the Hubble Space Telescope, we've discovered the accelerating expansion of the universe, imaged distant galaxies in stunning detail, and have even captured glimpses of exoplanets orbiting other stars. This is not really possible from the surface of the Earth. There are some observatories placed high up on mountaintops and stuff like that. That does make it a bit easier to view because you are starting well above major viewing points, I guess, from cities and stuff like that. So you're through part of the atmosphere already. So the higher up you can get in or on Earth to set up one of these observatories, the better off you will be. So space telescopes don't just answer scientific questions, they actually ask new ones. So what's out there? How did it all begin? Are we alone in the universe? These tools are cosmic detectives. Absolutely. So let's talk a bit about the history of space telescopes. So, the idea of a telescope in space started back in 1946, when Lyman Spitzer, an American astronomer, proposed placing telescopes above Earth's atmosphere to avoid its blurring effects. It took decades of engineering and innovation to make that vision a reality, leading to some of the most iconic space telescopes in history. So let's explore their stories. Orbiting Astronomical Observatory 2, OAO-2. Launched in 1968, OAO-2 was the first successful space telescope and precursor to modern observatories. Nicknamed Stargazer, it was designed to observe ultraviolet light, which is impossible to study from Earth. OAO-2 provided groundbreaking data about hot stars, interstellar gas, and atmospheres of other planets. While primitive by today's standards, it proved that space telescopes were not just a theoretical concept, they worked. And a good example of this is the Hubble Space Telescope back in 1990. So actually Hubble is still out there today, but we'll go a bit more in detail in a bit. So, arguably the most famous telescope, Hubble, was it has transformed our understanding of the universe. It weighs 11 tons. It's about the size of, say, a school bus, and it orbits about 547 kilometers, or that's 340 miles above the Earth. So if you remember from one of our previous episodes, that is in low Earth orbit, or LEO. With its 2.4 meter primary mirror, Hubble captures images in the visible spectrum, ultraviolet, and near-infrared light. Its discoveries include the pillars of creation. And just before we go into that, I highly recommend you go and look up images of these different discoveries. They are absolutely incredible, especially if you like any type of deep space photography or anything like that. I'm sure you've already heard of these, but can never get too much of them. So definitely go take a look if you haven't seen them. Very incredible. So yeah, the Pillars of Creation, a stunning image of star-forming regions in the Eagle Nebula. The Hubble Deep Field, a long exposure image revealing thousands of previously unseen galaxies. Evidence of dark energy, a mysterious force accelerating the universe's expansion. And now for a fun fact, Hubble's initial launch wasn't flawless. Its primary mirror had a defect. It caused blurry images. A 1993 servicing mission by astronauts aboard the space shuttle fixed it, turning Hubble into a legend. Yes, that is very true. So, Chandra X-ray Observatory, 1999. Named after Indian-American physicist Subramanian Chandrasekhar, and if I pronounced that incorrectly, my bad. Chandra observes the universe in X-rays, which are emitted by high-energy events like black hole collisions and supernovae. Chandra orbits far beyond Earth, up to 139,000 kilometers, or 86,500 miles, to avoid interference from Earth's X-ray absorbing atmosphere. Yes, that is right. Our atmosphere absorbs X-rays, and is another reason why we are unable to take those images from here on Earth, another reason why we put these observatories or telescopes in orbit and beyond. So key contributions here. Discovery of the largest known black holes. Observations of supernovae remnants, such as Cassiopeia A, showing the aftermath of massive star explosions. Mapping of galaxy clusters, which are influenced by dark matter and dark energy. And now a fun fact about Chandra. Chandra's mirrors are coated in a thin layer of iridium to help focus X-rays, which are notoriously hard to reflect. Alright, next, Spitzer Space Telescope, 2003. The Spitzer was designed to detect infrared radiation, which reveals objects too cool or obscured by dust for visible light telescopes to see. Its main mirror was made of beryllium and kept at extremely low temperatures using liquid helium to minimize interference from its own heat. See, these are a lot of different things you have to think about when building something like this, especially in the harsh space environment. Who would have thought that you have to protect it from itself? Its own heat can cause issues. So, some of the major achievements here. The first detection of light from an exoplanet. That's pretty cool. Insights into star-forming regions like the Orion Nebula. And this is a very cool one. So the Orion Nebula is one that you can capture here on Earth. Different wavelengths, you can see different things. So here on Earth, you're going to be invisible. But if you have any type of camera, even on today's cell phones, actually, they have a feature for some longer exposure. You can actually see the Nebula of Orion's Belt, which is super cool. All right, moving on. Observations of the Sombrero Galaxy, and it revealed its dusty halo. Spitzer was retired, though, in 2020. But its legacy lives on in the massive amounts of data it provided to astronomers worldwide. Now let's move to something a bit more modern. The James Webb Space Telescope, back in 2021. So this is a more modern one, also known as JWST. This is the largest and most advanced space telescope ever launched. Its 6.5 meter gold-coated mirror is over 2.5 times larger than that of Hubble's. It allows it to collect far more light. So operating at the L2 Lagrange point, 1.5 million kilometers, almost 1 million miles from Earth, JWST stays cool and has an unobstructed view of the cosmos. Now, you may be asking, what is a Lagrange point? Well, I won't go too into detail on this one, but in a future podcast, I will talk about Lagrange points and gravity and different effects. But you can think of a Lagrange point as a stable point between two bodies in space, or more. We'll talk two bodies, that you don't have to worry about either or pulling that spacecraft towards that physical body. So think of it as a balancing point between the two. So by putting a space telescope there, that is where it will stay while the two bodies do their little dance in space. But we'll go more in detail on that in a separate podcast, because we could probably talk about that for an entire episode. So let's continue on. So, JWST specializes in infrared light, peering through cosmic dust to study the formation of stars and galaxies in the early universe, the atmospheres of exoplanets, potentially identifying signs of habitability, the life cycle of stars, from their birth in stellar nurseries to their explosive deaths. And another fun fact, which some of these might not be too funny, but they're cool fun facts. JWST's launch and deployment were one of the most complex engineering feats in history. Its sun shield, as large as a tennis court, had to unfold perfectly in space, a process with over 300 potential points of failure. Think of origami, and I believe this was the one that they actually brought in or use origami specialists to help determine how to fold different types of, say, shields and that, so that they can fit them in very small places. There's like a whole art of folding, which is pretty cool. You can probably look up on YouTube or something and see some pretty impressive geometries in that are folded up that expand into pretty cool shapes and different sizes as well. So just wanted to point that out. So each of these telescopes have contributed to something unique to our understanding of the universe. So from ultraviolet light to X-rays and infrared radiation, they've opened new windows into the cosmos, unveiling its secrets one wavelength at a time. And the best part, the era of telescopes is far from over. With missions like Nancy Grace Roman Telescope and the European Space Agency's Ariel on the horizon, the future of astronomy is brighter than ever. Yes, there is so much more to see, and if you're someone like me who can literally stand outside an entire evening bearing cold or heat, I've done it in the Texas desert or in Florida, you can spend hours and hours on end looking up. So being able to have these feats of technology in orbit and beyond, capturing impressive and incredible images that I could stare at them for hours and hours on end. But yeah, so lots and lots of possibilities out there, and very exciting to see where things go. So let's talk a bit more about how these space telescopes are actually made. So designing a space telescope is like building a Formula One car and a Swiss watch at the same time. Every detail has to be absolutely perfect. Let's start with the mirror. So the primary mirror, often made of beryllium or lightweight materials, must be polished to an atomic level of precision. For JWST, it is segmented gold-coated mirror allows it to capture faint infrared light. Instruments, such as cameras, spectrometers, and sensors, are specialized for different wavelengths. Engineers design them to withstand the harsh vacuum of space. And it's not just the vacuum, it's the radiation environment and other things you have to worry about, like arcing between components from plasmas and all kinds of stuff. It's things you would never even possibly think about that become a reality in the space environment, which we will also talk about in another episode coming up in the coming weeks. So, thermal control is one of those things you have to deal with. So space telescopes need to stay cool. JWST, for example, uses a multi-layer sun shield to keep its instruments at around negative 233 degrees Celsius or negative 388 Fahrenheit. Now, launch considerations. Every component must survive the extreme vibrations and forces of a rocket launch. Think about folding a delicate machine like JWST into a rocket and then unfolding it perfectly in space. It's nerve-wracking feat of engineering, absolutely. And another fun fact about this one, if you look at a rocket launch and you watch it, you see all this water being dumped down at launch. It's not just for cooling, but it also dampens the sound, which helps alleviate some of the vibrations at launch of blowing itself apart. So it's cool fact about the water towers you see next to those launch pads. All right, let's continue on here. Why do we put telescopes in space? So we kind of briefly talked about this, but Earth's atmosphere distorts light. That's more or less the main reason. So that twinkling we see in the stars and that, it may be charming, but it is absolutely terrible for astronomers and distorts your image. Why, when you take your own camera out, and especially if you're in somewhere tropical or somewhere closer to the equator where the atmosphere is actually a bit thicker, you'll find that taking pictures of the stars is pretty darn difficult here on Earth. So if we want to get those clear and better images, we have to place telescopes in space. That way we avoid atmospheric distortion and we have access to other wavelengths that are otherwise blocked by our atmosphere, like ultraviolet and X-rays. So for example, the Hubble Space Telescope sees visible and ultraviolet light, giving us clear, detailed images. The Chandra X-ray Observatory detects X-rays from phenomena that cannot be observed here on Earth. These telescopes allow us to see the universe as it truly is. So don't always believe what your eyes are seeing when you are looking through some sort of obscurity, especially like our atmosphere. So what are the role of orbits and Lagrange points? So we'll talk more in other episodes, but I do want to go a little bit in detail here, a bit more, just so that we have a better understanding as we kind of mention them throughout this episode here. So where a telescope is placed determines what it can do. Absolutely. So we talked about low Earth orbit, LEO. So Hubble operates in this area. It orbits Earth every 90 minutes, and it's close enough for maintenance missions, but still above most of the atmosphere. Yes, I say most. There is still atmosphere at these altitudes or distances above the surface of Earth. That is why you have to keep fuel on board, say like the International Space Station, to every once in a while give it just a little kick to bring it back up to its desired altitude. Otherwise, if you wouldn't do that, the very, very small amount of particles that are there will build up and continuously decelerate the spacecraft that is orbiting, and eventually it would actually end up coming back into the Earth's atmosphere and burning up, which is not what we want, at least not yet. So, yes, low Earth orbit is where Hubble lives. So next, geostationary orbit. This is rarely used for telescopes, but ideal for satellites that need to remain fixed over one spot. So we don't really have satellites there, but key to point out. Now the Lagrange points, this is the fun one. So these are gravitational sweet spots where telescopes can stay in a stable position relative to Earth and the Sun. For instance, the James Webb Space Telescope sits at L2, or Lagrange point 2, which is 1.5 million kilometers away, shielded from sunlight and Earth's heat. This gives it an uninterrupted view of our cosmos, or the cosmos. I guess we can't claim them all. But yeah, absolutely. So how do these telescopes actually work? Well, they're all going to be a little bit different, but we're going to break it down here. So, capturing light. Telescopes gather light using mirrors or lenses. So for example, Hubble uses a 2.4 meter mirror, while JWST mirror spans a massive 6.5 meters. Focusing and filtering. Light is focused onto instruments that filter and analyze specific wavelengths. Infrared telescopes, like JWST, can peer through dust clouds to study star formations. Data transmission. Images and data are sent to Earth via radio waves. These signals are received by giant antenna arrays like NASA's Deep Space Network, or DSN, and processed by scientists. Now what about communication or maneuvering these things? So, space telescopes communicate with Earth using highly directional antennas. Commands are sent to adjust their orientation, switch instruments, or calibrate systems. Maneuvering is done using reaction wheels. So these are flywheels, or a spinning mass inside the telescope. They spin to reorient the telescope without using any fuel. We do use thrusters, so they are used sparingly because fuel is always a finite resource when you're in space, at least up to this point. So these adjust position when reaction wheels are not enough. And then another fun fact, telescopes like JWST are so far away that commands take seconds to minutes to reach them. Engineers have to predict every move in advance. This is also true for a lot of space communication, especially if we're looking at like rovers on, say, the Martian surface. They have to send a list of commands in advance, let the rover kind of carry out those commands, and then through image feedback, they'll see where they're at and say, okay, let's predict our next set of moves, and away we go. And that's another reason why these rovers move very slowly. You don't want to, say, drive off a cliff by accident because you thought it would end up one way, and in fact, you ended up the other. So we move slow and persistent, and send these commands and get feedback so that we don't end up doing something we don't want to do, especially in terms of fuel-based maneuvers like thrusters, as it is a finite resource on these spacecraft. So let's continue on here. Why are space telescopes so important? So other than just for observing and people like you and I who are just fascinated by the cosmos, space telescopes answer fundamental questions about our universe. They've revealed the age of the universe, the existence of dark energy, and even atmospheres of distant planets. Without them, our understanding of space would be far more limited. Absolutely. So, these discoveries and everything like that from these space telescopes, I think, in my opinion, are absolutely incredible. However, very small to what actually is out there. We don't know the majority of what goes on in space. So I think there's a lot more research in that we're going to see over the next 100 years as we continue to advance technologies and reach farther beyond our atmosphere, our solar system, and start placing more deep space telescopes and that can really capture those images. So it's very exciting, and I really look forward to see what else we can find, as we learn to study things like dark matter and these atmospheres from distant planets. Maybe we'll be able to answer some more of these other questions of what else is out there. Are there other living beings on these planets? Is it a habitable planet? Is it somewhere that is maybe in reach of visiting as we work through some nuclear thermal propulsion devices and new future methods of transportation through deep space? So it's very exciting. Now, there's obviously other things we have to work through here to get past other, risks in that, such as the radiation environment, and that, especially for deep space travel, cosmic radiation, and that is very terrible for us humans. So we need to continue to progress and expand our reaches while advancing technologies to help keep astronauts safe for manned missions as well. But probes and stuff like that, and more deep space telescopes, I think, are really going to open up the entire universe to us and really show us some fascinating finds over the next 100 years. But yeah, so with that is a wrap on today's journey into the world of space telescopes. I hope these basics of what we talked about today help open and expand everyone's knowledge a bit. For those that didn't know much about them, and for those that knew more, feel free again, give feedback, let me know, and we can dive deeper into, say, a specific space telescope or a specific technology that makes these pieces of technology possible. So I hope you have enjoyed exploring how these engineering marvels help us unlock the secrets of the cosmos. If you like this episode, share it with a fellow space enthusiast, and don't forget to tune in day to day. I try to do these every morning, but definitely stay tuned and keep up with these, and let me know if you have any questions for sure. So until next time, this is AstroJake signing off. Remember, keep looking up, stay curious. Take care, everyone.